In these next few videos, I'm going to be covering a few techniques and a few just things that you might find useful whilst building machine learning applications. And in this video, I'm just going to start off with more activation functions and activation functions in detail, as well as where and when you might use them. And later on, in the frameworks part of the course, I'll show you how all of this will be implemented. First, let's get started with activation functions. A neural network without any activation functions is essentially linear regression. And you've already seen the two activation functions that allow classification to happen rather than linear regression. And these are called the sigmoid function and the softmax function. These activation functions are only really used in the final neuron of a neural network. So if we had this neural network where we had 3 inputs, and then we had 2 nodes in the next layer, 3 nodes in the next layer, and then 1 node in the final layer. And just for notation, this node is called the final node, as I'm going to refer to it. And these 2 layers of nodes are the hidden layer, because if you think about it, you only really see the input and the output. You don't really see what's going on in the middle. And there are going to be connections between all of these layers like this, and so you'll get something like this. And then the final node will make a prediction, and this prediction, without the sigmoid function, let's say, which looks like this, it converts values between minus infinity over here, plus infinity over here, to values between 0 and 1. And this allows for a logistic regression output. But let's say you were training a linear regression model. If you didn't have this sigmoid function before your prediction, then you would just get minus infinity to plus infinity, and that's your linear regression model. There are also 3 more activation functions that are used in what are called the hidden layers, and each of them have their own perks. And after showing you some of the functions, I'll also explain how they are used. And just to make it clear, these kind of activation functions I'm going to show you are used here and here and here, and they make a lot of things much faster to run. They also allow for non-linearity, which I'll explain later, and there's just a lot of bonuses having them in there. It just makes training much easier for the neural network. So first, let's look at something called the tan-h function. It's also, like, the full name is the tangent hyperbolic function. You don't really need to know that. All you need to know is tan-h. And it is essentially just a mathematically shifted version of the sigmoid function. And so it looks like this. Starts up there, down there, sorry, and ends up there. And here are asymptotes at 1 and -1. And as you can probably tell, it looks very similar to the sigmoid function, and it crosses at 0, 0. So just to clarify, the asymptotes mean the line, so this tan-h line, draws closer and closer to 1, but never really reaches 1. Technically does at infinity, but you can't really get to infinity. And the equation for this tan-h function is tan h of z, because z is what you're going to be passing into this function. If we go back here, what you compute in this node is z equals w transpose x plus b, and then you put that through a function such as tan-h and the other ones I'll describe, and then you send another output of that neuron off as an input to the next neuron, and that neuron, instead of using x to calculate its z, what it does is it uses the value predicted here as its x. And plus b. So it calculates that, and then so on, carries on until you get a prediction. And as I was saying earlier, the equation for tan h of z is equal to e to the z minus e to the minus z over e to the z plus e to the minus z. And for those of you interested in its relation to the sigmoid function, if you want to write it in terms of the sigmoid function, tan h of z is equal to 2 times the sigmoid of 2z minus 1. And the sigmoid equation I showed you earlier. Now, why does this actually work? If you think about the data coming into the function, which we have named z, it can have values ranging from minus infinity to infinity. So if we go back here, there's nothing stopping this equation right here with the input and the weights and everything to ranging from minus infinity to plus infinity. And without the activation function, these values are the inputs to the next node. And because of this, like this massive range of values, the node has difficulty learning good weights and parameters and bias for a good prediction, essentially. And just to explain this a bit more, an analogy that helps me understand this is, imagine trying to, just learning to catch pebbles, and then suddenly a massive boulder gets thrown at you. You're obviously not going to be able to catch that boulder or learn to, whilst it's coming at you. And in that same way, it's really hard for this next node, which I'll color in with orange, to learn weights and biases when the numbers getting thrown at it are minus 5 million, plus 800, then 0, then plus 9 to the power of 8, and something ridiculous. So in that way, what the tan h function does, it scales z down between 1 and minus 1. And this basically has the effect of, if we go to rock analogy again, that all the rocks and massive boulders get scaled to something between pebbles and small rocks. So this has the effect, like if we go back to the stones analogy, that now you're not receiving tiny pebbles followed by massive boulders. You're receiving tiny pebbles maybe followed by small rocks and so on. And there's a limit to the size of the rock, which is shown by the asymptotes. This makes it a million times easier. Not exactly a million, but you get what I mean. It makes it much easier for the next layer to learn the best weights and biases for your predictions. And this function also has an added bonus due to its non-linearity, meaning the graph is basically not a straight line. It just doesn't do z equals wx plus b, w transpose, sorry. And I'll talk about why non-linearity is so good later on. Next, let's go on to the ReLU function. The ReLU function is short for the rectified linear unit, or it could be units, I'm not sure. And it is the most widely used activation function, and arguably the best one. The ReLU function looks very, very simple. It looks like this. So you have a straight line that represents y equals x here, and then a flat line here, where just y equals 0. And the equation for the ReLU function is ReLU of z equals max of 0 comma z. And this just takes the bigger value. So if z is somewhere here, like minus 8, it will choose 0. And if z is greater than 0 or positive, then it will choose Z. And then this very middle point here is simply just 0 because max of 0, comma 0 is 0. There are slightly different advantages to this ReLU function than the TANH function. The main advantage is very easy and quick computation. It is much, much faster than TANH because TANH requires all this kind of e to the power of something, exponentials and all that, and it's very, very curvy and non-linear. Whereas ReLU it's still non-linear, but it allows for very easy computation because it's just max. And also, a great thing about it is when you get bigger neural networks, it gets very, very hard to compute all the derivatives and go backwards and all that. This in a neural network is referred to as backward propagation, if you ever come across it. And the forward part is called forward propagation. And it's very easy to calculate the derivative of this because the derivative of ReLU is either 1 or 0. Because if you are to the right side of 0, then your gradient is simply 1, and if you're to the left side of 0, your gradient is 0, because the change in y, so the change in y over the change in x equals 1, because every 1 you move across in the x direction, you move up 1 as well. In the same way, to the left of the graph, the difference in the derivative is basically 0 because no matter how much x you change, you never move up or down. And there is also a variant of the ReLU function, which is called, which is a third activation function that I'm going to talk about, and it's called the leaky ReLU. And it's very clear once you see it. It's the same as the ReLU function here, but then instead of being 0 all the time when it's left of x equals 0, it just goes slightly down. And the equation for this graph is ReLU of z, sorry, I should say leaky ReLU of z is equal to max of 0.01 times z, comma z. So here it either takes 0.01 times z, or it takes z. And basically it takes this left value whenever z is less than 0, and this value whenever z is greater than 0. You can probably figure that out. And it has certain perks that the ReLU function does not, but because the reasons for that are quite complicated, and I am not that kind of advanced in this particular field, I won't really cover that now. But if you guys do want to learn about it, please do let me know, and I'll do some research about it. Right, now the non-linearity of these functions. What this really allows is for your neural network to fit more complex data better. So if your data isn't straight lines or just a simple curve, and if it has, let's say, you have data that looks like this. Sorry, I kind of neglected the graph, but let's say your data looks like this and you have classes here. You clearly see a relationship where this kind of data is in the middle. Sorry for the bad kind of plotting, but you kind of get where the data is. Here the data is kind of in the middle, it's in a circle. And without using activation functions, it's really, really hard to predict a classification boundary like this, where inside here the label might be true and outside might be false. And activations basically allow for this kind of stuff. Just as a note, when implementing an algorithm, the general rule I would recommend is basically just use ReLU all the time, unless you have a good reason not to, except in the very final node, because here you're making the prediction. And if you're using classification, you should put sigmoid or softmax. If you're using linear regression, you should not put an activation function at all. It really depends on what kind of algorithm you're using. And if you're using softmax, you should also bear in mind how many classes and all that. Now I'll explain where and how the activation functions will kind of fit into this neural network shown. Let's take a look at the top left node. This kind of top left node, I refer to this node right here, will look like this. You will have 3 inputs to this node, and then you'll have 3 outputs. And a node here has 2 main parts, calculating Z, then calculating A. So a node would look like this. First, it calculates Z equals W transpose X plus B, which is taking all the inputs, and W transpose X would be carried out 3 times if you're thinking about kind of non-vectorized implementation. So it would be weight 1 times first input, weight 2 times second input, weight 3 by third input, but I'm just doing it all vectorized so it's simpler. And then you would have to create an activation, so what you send to the next layer. And this is where I got the variable name A. It means activation. And just for this example, let's use the value. And then here you calculate A is equal to the value of Z. And you send this A off to the next layer where it is used by this next node to calculate W transpose A, let's say, plus B, and this A comes from the previous node, and this node uses this A to calculate its A, which is value of Z again, and then so on and so on. And then for the last layer, you do the same thing, but with softmax or sigmoid in the case of classification, as you want a value between 1 and 0. And for linear regression, you just put no activation at all on the last node, as you do not really want values between 1 and 0, you just want between minus and plus infinity. Of course, you would also need to change the cost function for linear regression and all that. And that's it for the activations. In the next video, we'll be going over some general techniques that will help you out a lot whilst making machine learning applications.